Can you see the screen?
Yep.
Okay. So yeah, I'll guess I can start. Hi. My name's Marvin. I'm an undergraduate at Harvard studying CS and math. Today I'm going to present some joint work I did with Professor Sitan Chen at the Harvard School of Engineering and Applied Sciences. A project on critical windows. It's a non-asymptotic theory for feature emergence and diffusion models. I feel like there's been a lot of recent interest in this topic, and I'm pretty excited to share my work with you. It's also just got accepted into ICML 2024, so
Oh, okay, cool.
yeah. So I guess I'll see any definitely give me some recommendations for fun things to do in Vienna. Um,
Oh, we shall meet up. I'm also going.
um, yeah. So, before I begin, I just want to give like a quick overview of diffusion models. So they're just general algorithms for sampling from high-dimensional distributions. So we see this, they've been used in like different contexts, like OpenAI Sora for video generation. Even Stefano Ramon has come up with like a new diffusion for text generation, for coming up with robot movements for planning, and even recently, AlphaFold 3, DeepMind's new model that predicts different protein interactions is also a diffusion model. So it seems like it'd be useful for all sorts of these different settings. So in general, they consist of a forward process which progressively transforms samples into pure noise, and a reverse process which undoes its procedures. So from this diagram, we start with an image, and then we selectively add more noise and noise. Uh, it turns so basically we kind of know the q of xt given xt minus 1. We know how to denoise it, and then to find out the reverse process, the reverse of this, going from a noisy image to a denoise image, q of xt minus 1 conditioning on xt, that is unknown. So we parameterize it with some theta, p of theta, and this is what we learn in a diffusion model. So just to give some details of what we consider, we look at in particular the Ornstein-Uhlenbeck forward process. So basically, you kind of with respect to t, you dilute the original signal x0, and then you add back some Gaussian noise to normalize it. And I kind of get some intuition for why this works is if like x0 is initially some normal 0, 1 Gaussian, then throughout the entire thing, it's also a normal 0, 1 Gaussian. It turns out that like if we want to look at infinitesimal changes in this one, you can write it as the following SDE: dxt equals to negative xt dt plus square root 2 dbt, and where dbt is just the standard Brownian motion. Now, in terms of the reverse process, it actually turns out that there's a true reverse process which generates the same marginals as a forward process up to some test functions. So the below equation there, um, uh, like basically, if you run the reverse process from like pure noise to get an original image, then you're able to generate the same marginals and generate an image at the end. Now, in terms of the components, one we have like an xt term. So this kind of you can see in the original forward process, you kind of dilute the image, and this xt one is kind of expanding it. And then you include this other term, this 2 grad log qt minus t. This is what's called the score. So it turns out learning like this central component is all really need to do the reverse process. There's also again the Brownian noise at the very end. So how do we so what we want to compute is a score. So how do we actually compute the score? So it turns out Tweedy's formula relates this problem of computing the score to the problem of denoising. So let's say I give you some x from some unknown distribution and some a noisy sample g, and I give you x plus sigma g, and to produce some noisy sample. If you want to compute the conditional expectation of x given its noisy version, right? Then it just turns out that you basically just take the noisy version and you include some small term that represents getting closer to the score. That moves you closer. You include some small term, which is just the score. Now, what this tells you is that if you want to learn the score, what you can just end up doing is asking it to minimize the expected L2 error of this denoising problem. So you give it a model some noisy sample, and you ask it to generate the denoise sample. and you want to ask it to approximate it in the original image in like L2 error. So uh, uh, like, and it turns out because this is the conditional expectation, the minimum is achieved at by the function that uses the actual score. So basically, you give it this denoising problem as an example, and then it basically just solves it to estimate the score. Yeah. So now I'm going to describe an empirical phenomena that has been noted by a lot of different authors, like I think that features of generated images like class, color, or background seem to arise in narrow intervals of the time reverse process. So let's look at the very leftmost plot by Georgiev et al. So we have a CFAR10 trained diffusion model, and we train a diffusion model to generate images of it from t equals 1,000 to 0, right? We can, and let's say we start with an image, we generate a horse, right? If we see what it was at like t equals to 600 and then start sampling from it, it can generate all sorts of different things. It can generate horses, cats, or whatever, right? But if we see what it was at t equals to 400 or like 500, right? And you sample it, it's always a horse. Sample from it. It's always a horse. Now, in terms, this phenomenon has appeared in a lot of different models, both times CFAR10, MNIST, like the problem left showed that this happens for MNIST. You can also, based on different measures of similarity as well, MNIST, ImageNet, and also ELSUN database. The rightmost plot shows that like you can see that this jump appears for all sorts of different measures of similarity as well. It's also been observed that earlier time steps of the reverse process seem to be responsible for larger scale features. Like this original observation should be credited to like Jonathan Ho in his like first paper on one of the original papers on diffusion models. And like the later steps of the reverse process seem more responsible for like finer details. It's also been observed by a lot of different authors that if you take like an image, if you take an image and you noise it to like different time steps, and then you denoise it, you also see these critical windows for different amounts of noising. So I guess like why might you be interested in this? So like there have been a lot of applications for this. So for the noising and denoising thing I described, like it's been used by in SD edit to for image editing and census. So you give it some sort of base image, and then you want it to modify but be based off of that. You can do this by noising and denoising the original image and blurring out some parts of it to varying degrees. Another thing it's been useful for is improving sampler schedules. So maybe it makes more sense to focus where you're sampling the diffusion model, where you're like training the diffusion model. You're producing more samples on spaces where it's deriving more perceptually important features. So like in the more larger scale features. It's also useful for localizing data attribution for diffusion models. So Georgiev et al. They try to apply data attribution for diffusion models, and like this is a very expensive technique. So if you're able to localize it to a few time steps, and then to determine diffusion, determine data attribution, then this is like makes your method a lot more efficient. Yeah. So I'm going to give like a quick overview of like prior work and give some like kind of intuitive descriptions of our results. Then I'm going to go into our results in more details, and then I'm going to give like a quick proof sketch. Yeah, excuse me. Yeah. So this by both prior and concurrent work have discussed this feature emergence phenomenon, but mainly from a statistical physics-based perspective. So Ryan, Brangioni, Sclocchi, and Baroli have all kind of discussed it. So just to give a quick overview, Ryan and Brogi gave an end-to-end asymptotic analysis for a discrete distribution supported on 2 points, and they link it to like flips in the signs of the of the of the Jacobian of the score. Sclocchi et al. They model their data as a random hierarchy model, and they kind of give accurate predictions for when these intervals of the denoising process occurs with a mean field approximation. Baroli et al. They also compute this like kind of phase transition, the location of this critical point, by applying a perturbative calculation that's usually used to predict second order phase transitions. Yeah. So like just in general, like these estimates are like are either like asymptotic or they're non-rigorous. By that I mean is that they aren't proofs for why the diffusion model should behave in a certain way up to this certain interval. They also require very strong assumptions on the data, that the data be Gaussian, or like their Dirac delta functions, which aren't really true in practice. So I guess in this work, can we find a rigorous explanation, so a proof for feature emergence of diffusion models, so for why they occur for a general family of high dimensional distributions. So that's the main like contributions of this work. So now I'm going to describe our data as it's set up. So we kind of ignore. So we assume we assume that we're dealing with the diffusion model's true score. So that's doing some score matching, and it has produced this real score in this like outputted distribution. So the distribution P is a distribution that's given when you like generate images from the diffusion model. So let's assume it's a mixture model. So it has components P1, P2, all the way up through Pk, and we let the means be like mu I, and then we have mixing means Wi. So we have a mixing weights Wi that sum to 1. So this is how we're setting up the data. We also define these different quantities. So we have W overline. This kind of represents like the maximum distortion in the mixing weights. We also have this term overline R, which demonstrates like the largest magnitude of the means. It'll be useful to keep in mind the width between S target and S init. So just between two sets, what's the largest distance between means? And then also the nabla S target. So like given a set, what's the closest mean from something in the set and that's outside the set? Yeah. It's also going to be useful to define a submixture. So like for example, let's say we have a model that generates pictures of like CFAR10 or mammals. Pictures of mammals, generations of mammals. A submixture could be the distribution of cats. So and the submixture is a cats, and itself is a mixture. So you can have orange cats, brown cats, black cats, etc. And to deal with the normalizing weights, we just basically define it to be like a normalized version of this. So we use P superscript S to denote like this distribution. Yeah. So in this paper, we consider the targeted reverse process. So it's a modification of the reverse process. So let's say we start with some S init and S target. So so we draw a sample from S init, right? Then we run the forward noising process to time T hat to produce some sample like X prime. And then from this terminal T hat, we run the reverse process with a score function derived from P. So we use the diffusion model's learn score function. And we want to see when this distribution samples represent PS target. So we're basically so we want to find critical windows for this T hat kind of phenomenon, right? So when we noise and denoise, let's say to some small amount, like some key features are maintained the same, and when we noise and denoise to maybe T hat equals to 1,000, some feature is not the same. Yeah. So just to make this more concrete, okay, so let's let S init be the submixture of orange cats and S target be the submixture of cats. So we draw a sample from the orange cat from the thing on the very left, right? And then we run the forward process for time T hat to produce X prime. So this is now the noisy version of the forward cat. And then from terminal time T hat, we run the reverse process with a score function derived from P. So we use this to produce a picture of a white cat. So like we can imagine that S in is a submixture of orange cats and S target be just a submixture of cats. And we're trying to figure out to what level we need to noise it to get the submixture of all cats. Now, intuitively, there are two kind of things that we care about with respect to this. One is we want to consider T lower. So this is the first time in which the samples from S init and S and S target become close to each other, right? So like we want to make sure that those samples are close to each other, right? So we need to run the noising for at least that amount of time. At the same time, we don't want to run it for too long, because if you run it for too long, everything kind of clumps together. So you want to make sure that the components of S target exhibit like like negligible impact up to, so we want to noise it up to a time where S target is still separated from everything else in the distribution. So let's say we've given some t hat and some t lower and t upper, and a mixture of strongly log concave distributions p, running the forward process from sample ps init for time t hat, and the reverse process for time t hat will reveal a distribution close to ps target and total variation distance. Now, strongly log concave distributions are just distributions where if you take the log of the PDF, they're concave. This might seem like a strong assumption at first, but it turns out that like this is resolved in a very small part of it of a lemma, and that lemma is actually much stronger than what we need. So we can kind of, it's not that important. At the same time, we can, when S init equals to, we still need T lower to be less than T upper to make this kind of a valid thing. And it turns out that this is true when the features are salient, which is in some sense, which I'll define later. Also, if S init and S target are the same, which is actually kind of useful for interpretability purposes, then we only need T upper to be greater than 0. So now I'm going to talk about the results in more details. So just for the notation of the mixture model, we let X superscript st denote the forward process when you start from p superscript s. So when we take a sample from p superscript s and we noise it, we generate samples x superscript s, and we let p superscript s denote the lull of xst. And for some, it'll also be useful to do some arithmetic over the path measures, so like probability distributions over paths. So if we have if we noise to some intermediate time t t hat, then we let the path measure of x superscript s be p superscript s t hat. Yeah. Again, the forward process is the Ornstein-Uhlenbeck forward process. So now we do we give some notation for the targeted reverse process. So so we're taking a sample from some s inits. We define this to be x bracket s s. So this is our sample that we take from the noised sample from S and the targeted reverse process, and then we run the reverse process to derive with the score from P to obtain X bracket S, and we let P bracket S be like the lull of this. Note that P bracket S is distinct from P sub S because we are using the score from P in the reverse process. Now, if we were to use the score from P superscript S in the reverse process, then we would just generate PS again because these two things are equivalent. But the difference here is because we're noising and denoising with like the full diffusion model, we're using the score of everything, including the like a score of the entire distribution P. Yeah.
I'm sorry, I didn't fully understand. So what do you mean by the score of everything? So
yeah. So okay. So let me go back to this slide, right? So in the reverse process, right? The reverse process depends on Q, right? So like it depends on like the starting distribution Q that we start with, right? So if we start with P superscript S, like the submixture of all cats, right? The score, like the score function just depends on the submixture representing cats, right?
Yep.
But here in our case, when we take an image of an orange cat, we noise it and then we denoise it. We denoise using the full like distribution P, not just full distribution P. And we compare that if we were to that if we denoise with and this is different than denoising with like P superscript S, right? So in one case, you're using the score with respect to the distribution, the image over all models. But in the other case, you're using it with only with respect to like the score from the distribution with only cats. If that makes any sense.
Yeah.
Yeah. So just some assumptions for our theorem. One is we need strong log concavity, and we also need it to be strongly log concave in the sense that each of the components are concave enough. We also need that the scores are L Lipschitz. Now, this is a condition that's like really common. It's used in all theory of diffusion papers. And then we require fourth moment bounds on the values. And That's our assumption three. This is stronger than like the second moment bounds and other theory of diffusion papers, but still like I think pretty reasonable for real data. And in terms of the score bound, we need let's say we take a distribution from one other component of the score and we compute this. We take samples x from like component j of this j of p, and then you compute the score at I. We want that to be bounded. So this is a kind of a new assumption. Now, this is pretty reasonable if you like assume the data to be like this is true if you assume the data to be Gaussian, and yeah.
No, sorry, can you repeat? If you assume what to be
Like
Gaussian?
just to give concretely,
Well,
like if the
so
data is
why
Gaussian,
would
then
you
you can like
assume the
explicitly.
distribution to be Gaussian?
Yeah, sorry, what?
Why would you assume the distribution to be Gaussian?
Oh, this isn't a requirement in our theorem, but like this is just like just to give some intuition for why this is true, like why the fourth assumption is true.
Okay, but can you try to explain that intuitively? So the fourth power of the norm of the score.
Like you should view this as like kind of like the score is like well behaved, right? It's yeah, like basically this is some sort of regularity condition. It is a little weird. I will agree, but like this is basically some like kind of like regularity assumption on the score bound. And if we want to go into more details, it actually only appears in a pretty small part of the proof. And I can discuss that later.
Yeah, maybe later you can also try to discuss if there are in which cases will actually fail, because that will give us a bit of an intuition of the. Are you aware of cases where this assumption fails that could be of interest for?
Um, well, like I think like if some moments of like okay, so if you imagine like pi to be like parameterized of like e to the negative, like pi to be like e to the negative h, and like and h is some polynomial, and we if the moments of like pj it's some polynomial with degree higher with a sufficiently high degree, and like for those degrees pj don't really exist. If those moments don't exist for pj, then this could end up not being finite. But I would imagine for most like natural distributions that these are fine.
Okay, so but we do know that in a lot of situations this will not be finite for t going to 0, right?
For t going to zero, yeah. Um,
I mean, I assume for t different than 0, then it's almost never an issue. I would say yes. For it to be very weird to actually not be finite. But for t going to 0, this will not be finite in a lot of situations, simply
yeah,
because the
yeah,
score in
yeah,
itself will diverge.
yeah, yes. But if you add like a small amount of Gaussian noise, it should probably be okay.
But
Um,
that's your assumption. But okay, but your results are not asymptotic for t going to 0 anyway, right? So your results are. Do you actually need this to hold for t going to 0?
yeah. I think you need this to hold for t equals to zero. But I think even generally for like real life diffusion models, like if you look at the data, like if you look at the score itself, I think I believe this is like pretty like well behaved.
Not at equal to 0. T equal to 0, the only reason why it's well behaved is because you are dividing by the standard, because you estimate the noise and not the score. But if you were estimating the score, it will it will get tend to singularity as you go to 0. But of course, the network estimates the noise, and then the score is divided by the standard deviation, which goes to infinity at equal to 0 too. Every time the distribution of the data is not supported in the whole space, the score is singular at t going to 0. But in real situation in images, by any real approximation, the support of the distribution does not have the full dimensionality of the space.
Yeah, I agree with this. I agree with this. So I guess this is actually like so like I think the way to think about the behavior at t equals to zero is that diffusion models are learning something that's still like smooth that's still smooth near t equals zero, even though this isn't reflected in the true data distribution, is learning something that's like that's still like that is the real data, like, okay, that is a real data distribution, but you add some sort of Gaussian smoothing. Like, so it's close in Wasserstein distance, but you still include some amount of some amount of like if you view the image generations, okay, let's say it actually successfully learns a distribution, right? Like, let's say then I think a reasonable claim is that the diffusion model is learning outputted generations is like the true data distribution over images plus some amount of like very small amount of noise. Um, so that is learning the true diffusion process up to that point, and that's like close enough in Wasserstein distance to the true distribution over images because like it's yeah.
Yeah, I mean, in practice also you don't go to t equal to 0 because that's usually singular. So even in practice we stop the diffusion at some finite epsilon.
Yeah. So I guess like like if at T, like in this case, I guess instead of 0 being the start of the like, well, we're looking at the generated distribution over images. So like in practice, if like whatever you end up stopping, you're stopping at like t equals to epsilon or whatever, like that would be your distribution, and in that case, the score would be more well behaved in that sense.
But I don't understand why you need it, because your results would be for critical windows, which by definition will happen at a finite time, so not equal to 0. So why do you need regularity at equal to 0 if you want to prove a results that happen earlier?
Yeah, so the thing that so we want to prove that like if we noise and denoise an image of like orange cats, right? Like okay, so how we argue this essentially is that like okay, let's say the S target is the same thing as an S initial, right? And uh we want to show that excuse me. Um we did denoise up to T hat, like 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 they produce the same distribution. Like and T hat's like very small, they produce the same distribution. Now, I'm going to skip a few slides. So basically, what we have the scenario is like, let's say S target equals S initiate. We want to show that when we noise it, right, and then apply the diffusion, the reverse process with the entire score, the score over the entire P, versus one with the score over like over like the submixture of cats, right, that they are similar. So going to this is skipping. Yeah. So this is theorem 6. What theorem 6 is basically, let's say we have a diffusion model sampled over uh, like 0 to t, like sorry, you have you have two reverse processes, except one is initialized at like both of them are initialized at the same place, but one uses like b and bt, and the other uses bt prime as a score. So what Professor Chen proved, like this is the sampling is easy as learning the score paper, is that if the expectation from 0 to t is the same, if like you can bound the distributional distance between q and q prime, between generating with b or b prime, by the integral over the L2, the expected L2 distance between these two values. So the thing is, this bound requires from 0 to capital T. So that's like kind of the main thing. And
so, but okay, but in practice, let's say, because regardless practicality, do your results break if the data is defined on a submanifold? Because then you will get the divergence there, and there is nothing you can do about.
Yeah. They do define if it's defined on a submanifold. I suspect that like they would still hold on like if you have a submanifold plus a small amount of Gaussian noise.
Yeah, but okay, but I mean, that's cheating, right? Because that's noise is by definition time different than 0.
Sure.
So I'm just asking the question: does it hold for a submanifold, or is it just a proof that needs to be modified, or there is something fundamental that will go wrong in that case?
No, I think it should be pretty similar. So like the sampling is using the sampling is easy as learning the score paper here, theorem 6. They did deal with they did deal with the um like the case where like the data lied on some submanifold. So the only distinct so how the general argument would go is that you consider the case where you just have a small amount of noise added to it, right? You would show that these two things are similar when you start with that small amount of noise, and then you would be able to obtain a bound in Wasserstein distance between the between the data like if you take an image of a cat, you noise it, denoise it, like right at the last point, it's close in Wasserstein distance to like the output, and also close in Wasserstein distance to the case where you noise and denoise with just the cat score function, and then I believe that kind of argument would work.
Yeah. Okay. Yeah, but by the way, there is probably also a very large amount of cancellation. Why the score is divergent, you have a difference between two scores, and those two scores will be almost identical actually at the limit equal to 0.
Yeah.
Because basically, if the critical window is before, these two scores are almost identical. Probably they converge to each other at the limit equal to 0. So it's actually possible that the limit is finite. The limit of the expression is finite, even though actually I will bet that is the case. I will bet that the limit of expression is actually finite, simply because the two diverging terms will cancel each other out.
Yeah. Yeah. No, that's interesting. At least for us, like we wanted to keep like the topic like of the paper more like I think strongly log concave distributions are like a rich enough distributions that we can like I think they're kind of a nice intermediate step where like they still contain a lot of broad distributions, but they're all like they're not in any submanifold of the data, and they're still like quite nicely well behaved. So yeah, I guess I can go into the main theorem statement. So if we have T lower epsilon to be so again we introduce the concept of T lower and T upper. T lower basically just says, oh, we want to noise up to the time where the distribution of S target and S init are close enough to each other, and T upper says that we want to make sure that every component of S target is disjoint from the component of is disjoint from any component from a K minus S target. And what the bottom equation just says is if you just take an image from S init and you noise up to T hat and denoise it, and then we compare it to the case where you just start with S target, then the total variation less than epsilon times all these terms that we saw before. Yeah. Let me move to the next slide. So it turns out we can write these terms more concretely. So instead of total variation, we can operationalize them. So if we let pi overline to denote the density of the ith component when you mean shift it to 0, and then you let the Wasserstein distance between pi and pj be less than or equal to be bounded, right? That term is just subsumed inside the T lower by a T lower of the width of S init S target. So the farthest distance between means and S init and S target. And if you assume that each of these are sub-Gaussian with parameter sigma squared, then it turns out T upper can be lower bounded in terms of delta of the distance between things in S target and not inside S target. So you'll notice here that there's this dependence on dimensionality in this term, which is kind of ugly, and we'll remove that later. So just specialize in case with K-Gaussian identity covariances. A lot of these bounds simplify, and we get the following. So the T lower only really depends on the width of S init and S target, and T upper only depends on the width natural log of the S target and minus some double log terms. So in comparison for general mixtures, we're able to avoid this dependence on dimensionality D. Yeah, so just a quick proof sketch. So again, so we're starting with the case where we take an image, P bracket S, so S init. So we take an image from S init, we noise a time T hat, and then we denoise it, and we're comparing it to PS target. It's actually more convenient to compare the distribution path measures, and we can use the data processing inequality to achieve this. So we compare the distributions over paths that is induced by P bracket S init, and then the distribution with P S target. And we again use a triangle inequality to break it up into two terms. So we introduce this term PS target t hat. So just as a reminder, this is what happens when we take an image from S target, we noise it to time t hat, and then we denoise it using the full score. So the first term, you'll notice that the only difference is where we initialize at. So in one case, we initialize at S, and in the other case, we initialize as S target. So we then can again use a data processing inequality. We can abandon down it by the errors between, okay, if we initialize at S init versus at S target at time t hat, and that is less than equal to epsilon by our assumption on t lower. To recap, for the difference in 2, you'll notice that P bracket S target, this is the distribution when we start with S target, we noise it and we denoise it using this full score. And P T hat S target, this is if we just noise it to PT hat S target, and then we denoise it using the score only from S target. The only difference in 2 are the scores that we used. Are they from S target or are they from the full distribution K? And this is what we'll be focusing on. Term is the most difficult one to bound. So notice that the only thing we care about is score difference, and this has been studied previously. So Chen et al. In 2023, the Sampling is Easy as Learning a Score paper, they basically show that you can bound the KL between two distributions in terms of the integral over the expectation of the L2 difference. Now, they initially use this to kind of show that this shows that basically if you accomplish like the score difference minimization, then you if you're able to minimize the L2 well enough, then you basically and you learn the real score, then you've learned the real distribution. So using Pinsker's inequality, we can bound the TV between these two situations into the following. So just to be clear, we take samples from S target, we noise, and then we denoise them, and we're comparing the case where we use a score with respect to PT versus the score if we used a PTS target. Yeah. So to bound this term, we use this following inequality. Sorry, excuse me. So it turns out we can write the score of S target and just P itself into the score of S target minus the score of K minus S target times the ratio of the PDFs of K minus S target divided by K. So and then we use Cauchy-Schwarz to separate the expectation and expectation over each of these terms individually.
So wait, what is K minus S target?
So like the set containing all the components not in K but not in S target.
Okay, yeah. So
yeah. So like intuitively, like the first term is basically just saying why should we expect that to be small? The first term is just saying, okay, as we run it for a long enough time, right? The scores of everything kind of get closer and closer together. Yeah. And the second term is basically just saying the ratio of some x, right? Like the probability that it belongs. You can also view the bottom as like a conditional expectation. So you have some sample xt sampled from pt, right? What's the probability that it belongs to K minus S target? So you can see if like S target is separate from everything else, that this is like probably pretty small. Because yeah. So like if we have an example for like an image of cats, right? Like if we have an image of cats, right? And we noise and denoise it, and we add a little bit of noise, right? The conditional expectation that it comes from the cat class is already pretty high. Yeah. So now I'll describe how to prove the first term in both first terms in more detail.
So it's the weighting term should be like a probability ratio, right?
Yeah, it's a probability ratio. Yes, it's a conditional probability.
That's funny. We are using basically the identical formula in our current project. We are currently working in removing some classes from a diffusion model.
Like for what purposes? For like
just for removing. Just let's say that you have like an image that you don't want the model to generate anymore. Maybe it's inappropriate, or so then you need a formula for actually removing that specific class from your model without retraining the score. So actually, we end up using your very same formulas for that.
Yeah. The score of a mixture model decomposes quite nicely.
Yeah.
Like it's like this weighted sum. It's like it is a conditional probability times the score of each of the individual components.
Yeah.
Like I'd be curious. Like, do you want to like? I'd be curious in talking after to.
Yeah. Let's finish the presentation and then we can discuss it.
Yeah. So the key to bounding the first term is basically you can show that like the expected difference between two L2 scores decreases exponentially. So for t is less than 0.01, we have to use our assumption for. Basically, we want to make sure that the scores are kind of like well behaved at the starting process. And for t greater than equal to 0.001, we compare the score to the score of like the normal zero identity matrix. Yep. Yeah. Now to bound that, it turns out that we do some sort of differencing trick. So it turns out like we can actually bound the Hessian of a strongly log concave function approaches the identity matrix as t goes to infinity, and because it approaches the identity matrix, the distance between the score evaluated at 0 and x, it becomes close to the difference between evaluated the normal score at 0 and x. And and both of these terms end up going to 0 exponentially quickly with respect to t. Yeah. In terms of bounding the second difference, we use some simple algebra. So it turns out that like if you draw a sample from P and then you compute the ratio of the PDF Q over P plus Q, right? That can be bounded by various measures of various F divergences. So most importantly, the very rightmost one, if the total variation between these distributions is like close to 1, then the ratio is small. This makes a lot of sense intuitively. And I won't show the algebra here, but basically, based on our T upper bound, based on our T upper bound, like based on our T upper bound, like well, the total variation is like guaranteed to be like epsilon squared over 4, and everything cancels out very nicely, and we get that this ratio is like less than equal to epsilon. Yeah. So to deal with the cases with general mixtures of several components, to write T lower in terms of differences, we want to show that like if we run it for enough time, total variation from different components come closer in together. We require that we're able to do this by bounding the KL between these two things, and we bound the KL between these two things using some Wasserstein smoothing between the components in the initial and target subsets, and that decreases exponentially quickly. To write T upper, we just use sub-Gaussian concentration bound. So when you run the diffusion, when you don't noise it too much, the components of S target are far away from other components just by sub-Gaussian concentration bounds. For K-Gaussian identity covariances, it turns out the key to this is solving this quantity here, like the ratio of the covariances. And for the quantity, I like put a red box around. This is in terms of Hellinger distance. So we write this quantity in terms of Hellinger distance, and it turns out that there's a simple AMGM cell inequality that allows you to simplify that. For matrix determinants, that allows you to simplify that. Yeah. It turns out this can use a motivated membership inference attack that has like non-negligible performance, and like a private. So yeah, and then just to give some takeaways generally, we prefer to kind of revive rigorous non-asymptotic bounds for critical windows in which features emerge through noising and denoising. You can write these bounds in terms of inter and intergroup measures of separations, and we can instantiate these bounds for well-conditioned Gaussians. Thank you so much.
Thank you very much.